Good morning, class. We are looking at section 2.5, continuity. Okay. So we covered the tangent and velocity problems in this chapter, the limit of a function, calculating limits using the limit laws, a precise definition of a limit. We're going to go to continuity. And we have the definition of a limit at the bottom, and we're going to take it from there. So let's look at this page. This is what we have covered, and we're going to move on from here. Okay, class. The limit laws, okay, direct substitution, one-sided limit, the squeeze theorem, and direct substitution that has been already discussed, and that works for continuous functions. All right, we have the precise definition of a limit. Whatever epsilon larger than 0, there is delta larger than 0, such that if absolute value of x minus a is less than delta, then absolute value of f of x minus a is less than epsilon. So that's something we have seen, nothing brand new, and we are going to move on. Here's the summary of continuity, class. The shortest version I can tell you is that there are two things you need to do. You have to find the limit, okay? And remember, how do you find the limit? One-sided limits, if need be, limit from the left and right. And then the functional value. The only way the function is continuous, okay, if the two are the same. In other words, a continuous function is such that the limit exists and the limit is equal to the functional value. I want you to look at this one. This is the synopsis of the whole thing. Limit exists and it's equal to the functional value. And that's all there is to it. So, and we do the direct substitution because every function that we have studied is considered continuous as far as the course is concerned in its entire domain, meaning we should be able to come up with it. The next thing is the intermediate value theorem. You have seen this, we have discussed this in pre-calculus class. The IVT says the following: if there is a function which is continuous, okay, in some closed interval of a to b, okay, if it's continuous and you're dealing with a closed interval of a to b, let n be any number between f of a and f of b where the two values are not equal. There must exist a number c in a comma b such that f of c equals n. In other words, if it's a continuous function, it covers every point along the x-axis between a and b, and it covers every point along the y-axis between f of a and f of b. That's really the meaning of it. So that's the synopsis of what we have seen before in pre-calculus. So a function f is continuous at x equals a if, again, we looked at the summary, and this is a definition of a continuous function. So the limit exists. And remember, the limit exists if the one-sided limits are identical. And then the limit is equal to f of a, the functional value, okay? That's as far as the continuity goes. The function is continuous over an interval if it's continuous at each point of that interval, okay? And of course, if it's not continuous at a specific point, we say it's discontinuous at x equals a. So this is the basic definition, okay? So I hope everybody is following that. All right. So in short, the limit of f of x as x approaches a equals f of a, that means the function is continuous, okay? And this thing happens in real world, okay? The limit of the function as x approaches a. A continuous process is one that takes place gradually without interruption or abrupt change, okay? And the physical phenomena are usually continuous, okay? You can read this page on your own. The displacement or velocity of a vehicle varies continuously with time, okay, or a person's height, okay? Um, all right, so geometrically, a continuous function is a function whose graph at every number in its interval has no break in it. The graph can be drawn without removing your pen from the paper. There is no hole, okay, there is no break. You remember that definition from before. All right, so we've seen this. Let's look at some examples to see what happens, starting with this one. At which numbers is f discontinuous and why? I believe everybody can see the answer easily, but let's quickly have a discussion, okay? What you clearly see as a discontinuous point and why. Anybody can tell us what numbers seem to be the points of discontinuity at x equals what?
1,
1, perfect. What else?
3, and 5.
Beautiful. Let's discuss that. Obviously, as you look at 1, there is a discontinuity and f of, the limit does exist, okay, but f of 1 is undefined. If you look at 3, okay, it's, the limit doesn't exist, right? From the left and right are different, so that's why the discontinuity happens. It's a jump in essence. And in number 5, it is discontinuous, but f of 5 is also defined. So in a equals 1 or x equals 1, f of 1 is not defined. In the case of a or x equals 3, the limit doesn't exist, okay? Because the limit from the left and right are two different values. At a equals 5, we have a problem. The limit does exist, but it's not equal to the functional value. So this is important to understand. And those are three different cases, okay? Again, one of them, the functional value is not given to us. One of them, the limit is different from the left and right, so the limit doesn't exist. One of them, the limit exists, the functional value exists, but they are not identical. So look at this top value class. By definition, the limit must be equal to the functional value. And if they are not the same, the function is not continuous. All right, very straightforward. Is the above function continuous at x equals -2? Why or why not? Okay. First of all, class, if you have a case such as this one known as a piecewise defined function, you look at each piece. The top piece is a linear function, and so is the bottom piece. So this one, okay, y equals 1/2 x plus 3. This one, y equals x minus 1. A linear function is continuous from negative to positive infinity, so all is fine. You have to look at the end point, namely -2. So to see what's going on, we're going to look at the function and its limit from the left of -2, from the right of -2, and the functional value at -2. So let's evaluate those. The function value, g of -2, we go with the equality class, and we use this one, x minus 1, and we get -2. So this is the functional value. In other words, the right side here. Let's look at the limit. To look at the limit, we look at the one-sided limit. Left-sided limit, when x is less than -2, we are here, and we're going to use this piece. For left-sided limit, okay, 1/2 times x, we replace it with -2 plus 3, and we end up with 2. Right-sided limit, x is larger than or equal to -2, we go with this piece, we calculate that, we get -3. As you can see, obviously the limit does not exist. And because the limit does not exist, the function is not continuous at -2. Okay. I hope everybody's clear. However, some of you may notice something interesting, and that is the function, so again, the function is discontinuous at -2 end of this story. However, you notice that g of -2 and the limit from the right of -2 are the same. Then we say the function is continuous at x equals -2 from the right. Okay, so first the function is not continuous at x equals -2. Second, we add this piece, okay, coming up in essence. One-sided limit, one-sided continuity. Again, look at the fact that g of -2 is equal to the limit of g of x as x approaches -2 from right. Because these two numbers are the same, we say it's continuous from the right. Okay, class, I hope it's clear to everybody. Okay, we're gonna move on. All right. There are different types of discontinuities. You're looking at various functions and you're looking at their graphs, okay? And so we are dealing with a number of different functions. And we have the graph for the first one, okay, the second one, so on and so forth. So there are 4 functions for graphs. I want you to pay attention to the graphs. Look at the first one, okay? If you look at part A, there is a hold. That's a discontinuity. That's a discontinuity. That's a discontinuity. That's a discontinuity. What is the difference? This one is called a removable discontinuity. When the limit exists, it's called a removable discontinuity. Now, in this one, the functional value is not defined. You just have to redefine it. In this case, the functional value is also defined, but yet it's discontinuous. So you redefine it and you change it and it becomes fine. Both cases, because the limit exists, are called removable discontinuity. This one, there is no way we can fix it. Okay, this is a vertical asymptote or indefinite discontinuity. Infinite, my apologies, infinite. This is a vertical, basically you have a vertical asymptote. Now this one is a jump. In fact, you have infinitely many jumps, okay? This is the greatest integer function. Greatest integer function, you have infinitely many jumps. This is a jump. So we could remove the discontinuity in the case of the removable discontinuities, okay, by redefining them. And that's the main difference between the 3 types. So removable discontinuity, vertical asymptote, we write that. So VA or vertical asymptote, or we have a jump, okay? All right, so those are the type of discontinuities. Let's move on. Is this function discontinuous at x equals 3? We are seeing the same question, the same type of question, so you have to look at the limit from the left and right. You have to look at the functional value, and if the two are identical, then it becomes continuous. So let's find out. To take the limit as x approaches 3, because x is not equal to 3, that means from the left and right we use the same thing. So let's do that. We don't have to write 3 from the left and right. If this was less than or greater than, then we would, but not equality, that means from both sides of 3 we use this function. Okay. Except at x equals 3 we use 7. So with that being the case, obviously we get 0 over 0. We've done this many, many times, and the technique is to do what? Simply put, factor. X minus 3 and x minus 3 cancel each other. Replace the x with 2, and you get to the answer number 6. This is a limit And as you can see, h of 3 is equal to 7. So the functional value is 7. The limit is 6. So what's going on here? They are not equal. And therefore, it's discontinuous because the limit of h of x as x approaches 3 is different than the functional value. The two are not identical. The function is discontinuous at x equals 2. It's extremely important. Now, just in case, if the question was, how do we make h of x continuous at x equals 3? We have to redefine this as this. If we could change this number to 6, then it becomes continuous at x equals 3. Okay, class? In case that one is asked. So the bottom line is you take a limit and you take the functional value, you set them equal, and that takes care of the business. Here's the next one. First, here's some definition. I mentioned the definition of continuity on an interval. The function is continuous on an interval if it's continuous at every point of that interval. Okay. The other thing is that if we know a function is continuous, okay, at a specific point, then any combination algebra function is also continuous. Okay, algebra function. F is continuous, G is continuous, then F plus G, F times G. In fact, F of G, G of F, all of them are continuous within their domain. So all you have to do, be careful with the domain. A simple example. When we look at F over G, we always make sure G is not 0. So that's something that you got to pay attention to. And of course, polynomial functions are continuous everywhere. Any rational numbers, whatever is defined. So in short, every function is continuous in its entire domain. Let me actually write this. All functions or CTS, short for continuous, in their now domain, and I'm going to put it all caps. Meaning what? Meaning if you claim a function is continuous, you got to be able to come up with their domain immediately. For example, a polynomial function, the domain is all real numbers. A rational function, all real numbers except what makes the denominator 0. Okay, so I hope everybody's following this.
Professor?
Yes.
Quick question. What does CTS again mean?
Continuous.
Okay, continuous. Thank you.
Continuous. CTS stands for continuous. Thank you. All right. CTS, continuous. All right. Here's an example. This number is not given, class. You want to make it up such that this function becomes continuous. Okay? Very simple. The limit has to be taken. F of A, in this case, of course, number 5 is given as C. We set it equal to that, we're done. So all you have to do, take a limit, and whatever the value of the limit, you put it there and you're done. Okay, I hope everybody is clear as to how we arrive at the answer. Okay, class? So simple. Let's take a limit. When you take a limit, obviously, plug-in give you 0 over 0. We work with limits. We factor x minus 5 is in common. It drops and it becomes 10. It's a very simple process. That's why we've been working on the limits. So this becomes a piece of cake for us. So all you have to do, you say the limit is 10. You want f of a to be 10. That means you want f of 5 to be 10. That means c becomes 10. So if you choose that, the function becomes continuous. It's really that simple, class. Okay, I hope everybody is comfortable with that. Okay. All right. We're going to move on, class. So choose C to be 10. So you take a limit, you look at the functional value, you set them equal, and you're done. The two must be identical. So having said that, we are going to move on, okay, to the next part. Okay, I don't want to go through this. This is a repeat. And this is the theorem I was mentioning. Every function is continuous in their domain. Okay, pay attention to this, their domains. So what is the domain? Well, you should know the domain for every function. Okay, just for the sake of argument, if you're looking at the root functions, well, if the index is odd, it's all real numbers. If it's even, the radicand must be larger than or equal to 0. Just as an example, let me put that up for you so you see what I mean by that. If you have y equals cube root of x, I hope you see that the domain is all real numbers because the index is odd. But if you have y or f of x equals square root of x, then it's from 0 to infinity. So you got to be able to come up with that. That's the idea of domains. You have to know the domains, okay? All right. So, and any algebra function, any composite function will do the same for us. Okay. So if g of x, if you have a composite function, okay, therefore g of x. Okay, so because of this continuity, basically we do the plug-in. All right, is this function continuous? That's what we want to look at, class, okay. All right, let's see what we get. You just go with the limit laws, okay, and start with the limit. Basically, we plug in, remember that, but if they want us to prove that using the properties of limit laws, and we have seen that before, I have shown you how to use the limit laws. You have two pieces at top, two pieces at the bottom, okay, you separate them in that manner, okay. This is how the limit laws work. I hope you remember that, at least, you know, for a case like this. Now, you work it out and you get 14 over 5. And now you say this is the limit. What about g, going back to g, what is the functional value, what is g of 2? So we didn't want to plug in the first place, because if you're saying the limit is equal to the functional value, if you plug in, it's only the functional value. Now g of 2 happen to be the same thing, but this is the limit laws that gets us 14 over 5. G of 2, just plug in 2. Okay, so this is the way to go. Okay, class? All right. Find the limit of this one. They are not asking for limit laws or anything like that. All it is just plug in and observe. And that's what we are going to do. So replace the x with pi. Let's plug in. So sine of a pi here and so on. So we just plug. Now everybody, we know what sine of pi, right? Sine of n pi is 0 in general. So sine pi is 0. So you get sine of pi, and sine of pi is also 0. Okay. You don't need the n pi here. This is just pi, class. But I actually meant to remind you because, let me just, okay, in general, I'm trying to remind you that sine n pi is 0, where n is an integer. This one is simply sine pi, okay, class? Because this goes to 0, pi plus 0, and that's the case. So I don't want anybody to, mix it up. Okay. So sine pi is equal to 0. We're going to move on. We want to remove the discontinuity of the function at x equals 2. Okay. That means first we have to find the limit, and then we say f of 2 is equal to that. That's really the bottom line. To remove the discontinuity, you have to find the limit of this function. Okay. Let's find the limit. Okay. Now, to find the limit, we have to factor. I'm hoping that everybody remembers a cube minus b cube. Let me just write that for you again. I think I did it some time ago, but just to be on the safe side. Okay. A cubed minus b cubed is a minus b, a squared plus ab plus b squared. So factoring, okay, will do the job. And you take a limit of the factored form. You can start with the limit and factor it, or you can factor it and then put in the limit, in any event. When you take a limit, okay, and you want to take a limit of f of x class, you can start from here, simplify it here, put it in here now. Now it's time to put it in, plug in the values. And when you do that, you end up with 3. All you have to do, say, okay, I'm going to define f of 2 to be number 3. And it will take care of the business. Okay, it's pretty straightforward. All right. So, in short, find the limit and set it equal to the functional value. All right. Why is this function continuous at every number in its domain? It's important to see what the domain is first. I hope you realize that you're looking at the combination of a function, a sine, and a rational function. So the function sine is has a domain all real numbers. And the portion with the x plus 1 in the denominator, 1 over x plus 1, you can think of it. The domain is all real numbers except negative 1. So whatever makes the denominator 0, that means x equals negative 1 has to be excluded. And that's it. So if you're explaining something is continuous, pretty much all you have to do come up with the domain. Sine has a domain all real numbers, and the rational function like 1 over x plus 1, for example, has a domain all real numbers except negative 1. And so negative 1 is excluded from this. So trigonometric function sine x and the polynomial functions are continuous on R, that means all real numbers. When you have sine over x plus 1, it's continuous in its entire domain. The domain is all real numbers except what makes this guy 0. That's why we are excluding that. Now, a notation that is normally used here would be the domain is minus infinity, comma, negative 1 union negative 1 to infinity, okay, class, just in case. So I think that's really good to know. Pretty straightforward. All right. We want to show that this function is continuous from negative to positive infinity. Class, this is a piecewise defined function. F of x equals sine x. If x is less than pi over 4, and it's cosine x if it's larger than or equal to pi over 4. So what do? Very simple. Each piece, we look at them separately. Sine is continuous everywhere from negative to positive infinity. Therefore, this is continuous from negative infinity to pi over 4. Cosine, the same thing. Therefore, it's continuous from pi over 4 to infinity. So we have no problem except at the end point, namely pi over 4. So we will look at specifically pi over 4. Now, trig functions are continuous on negative and positive infinity, okay? Therefore, the function is continuous from negative infinity to pi over 4 union pi over 4 to infinity. In other words, this one class is continuous, CTS short for continuous, from negative infinity to pi over 4. Let me use a different color. And the bottom one, and by the way, why pi over 4? Because it stops at pi over 4. This one is CTS from pi over 4 infinity. I understand it has the equality, but the endpoint really doesn't count, okay? You can put, if you want, bracket, it's really not important. What matters is that what happens now at pi over 4. So everything is fine everywhere. The only question we have is pi over 4. So let's check what happens to the function at pi over 4. So we're going to take a limit and we're going to look at the functional value also. So let's check out the endpoint, namely pi over 4. Okay. If you take a limit of the function as x approaches pi over 4 from the left, class pi over 4 from the left, you have to go with the top piece. So you put the top piece. And everybody knows this is square root of 2 over 2 or 1 over square root of 2. By the way, let me just write this. Normally we use square root of 2 over 2 class, okay? Everybody knows that, okay? That's fine. Either way is fine. All right, now the second part. So that's the limit as we approach pi over 4 from the left. Now, from the right, we use the second branch, second piece, okay? So we're going to use cosine, all right? When we do that, as you know, sine and cosine, both of them at pi over 4 are equal to square root of 2 over 2. So the limit does exist. Also, the functional value, look at the equality. Why are we using the second piece? Because this one has the equality. Whatever the equality, wherever the equality sign goes, it goes with the first one or the second one. In this case, the second one. So the limit exists and it's equal to square root of 2 over 2. The functional value is the same thing. Therefore, the function is continuous at pi over 4. And because it's continuous at pi over 4, it's continuous everywhere from negative to positive infinity, because as you see, the question was just pi over 4. Everything else was fine. Okay. I hope everybody's okay with this. All right, the IVT, short for intermediate value theorem, was discussed in pre-calculus, and I put it in the summary when we started. And it's really important to understand what it means. You're dealing with a continuous function class. The function is continuous. So look at this function. It's continuous. If it is continuous, and it goes from A to B, for example, then it covers everything from A to B along the x-axis. Now, for A, we have f of A. For B, we have f of B. So it better cover everything from f of A to f of B along the y-axis. That's really the meaning of it. So the key word is continuity. This works only it's continuous. So if it covers everything from A to B along the x-axis, it covers everything from f of A to f of B. And that is helpful when we want to find the roots. Okay. If we have a negative and positive value for f of A and f of B, 0 is in between. So it crosses the x-axis and it does have a root. That's the idea behind this, okay, class? All right. Use the intermediate value theorem to show there is a root for this equation, okay? Now, first and foremost, you got to bring it to one side, and it doesn't matter which side, okay? We're going to bring it to one side, and we're going to give it a name, f of x. So when we say use the intermediate value theorem to show there is a root, that means solve the equation. Is there a solution in essence, right? So if there is a solution, okay, then what happens is this f of x, okay, bring it to one side. It doesn't matter which side, class. We are going to see whether it's continuous from 2 to 3, okay, first. And then we're going to evaluate it at the endpoints 2 and 3 and see what happens. Sometimes you have to figure something in between, by the way. Okay. Number one, this function is continuous from 2 to 3. Why is that? Okay, let's look at the function. I hope you see the domain piece by piece. This is a combination of a rational function, a linear function, and a square root. So if we were to write the domain would be zero to infinity. Let's see why. For this one would be 0 to infinity. For this one, x can't be 0, and for minus x there is no restriction. That's why the answer becomes this. So if the function is continuous from 0 to infinity, it is continuous from 2 to 3. I hope everybody is following what I'm doing. One more time. There are three pieces: a rational piece, a linear piece, and a square root piece. Square root piece gives us the domain of 0 to infinity. Because of the rational, we exclude 0, okay? And this becomes the answer. So this is your domain. We are interested from 2 to 3. 2 to 3 is in this domain of 0 to infinity. I hope everybody understands what's going on, okay? So with that being the case, we are going to evaluate the function at 2 and 3. So plug in 2 and plug in 3. Now you need, if you want to see what happens, you may have to use a calculator. The point is the following. One of them is positive. One of them is negative. We don't care what the number is. What we want is if one is positive, one is negative, 0 is in between. So this function f of x, okay, has to go through that. So f of x equals 0. So there is a number c such that f of c is 0 on the interval of 2 to 3 by IVT, intermediate value theorem. I can't emphasize this enough, class. So number one, continuity. So you've got to come up with the domain. Number two, recognize the domain that you are interested in. What did we want, 2 to 3, or, it's closed and it's between the 0 and infinity. 0 infinity contains that. That is important to see, okay? 0 to infinity, which is the domain of the function, contains what we want, okay? And the next thing is to look at a similar example as the last example for this concept. I hope everybody is comfortable with that. you come up with two values that are different. One is positive, one is negative. Okay. Therefore, there is a root of the equation. Remember, the function, when we say f of c is 0, is the same as saying the equation equal to 0. And that's what we were looking for, okay? There is a root for this equation. There is a 0 for this equation. Sine x equals x squared minus x. All right, the very first thing is to figure out the domain. So we bring everything to one side, and which side it really doesn't matter, okay? So you can say x squared minus x minus sine x, or sine x minus x squared minus x makes no difference, okay? We bring it to one side and we give it a name f of x, okay? Again, doesn't matter which side. And this function is continuous. Why is that? Well, if you're claiming it's continuous, you got to be able to come up with the domain. So let's do that, class. This function contains a polynomial function here. This is poly, short for polynomial, right? And then sinusoidal function, trig function. And the combination gives us no restriction whatsoever. Domain is all real numbers. So the moment you say continuous, it's fine, come up with the domain. So the function has a domain which is all real numbers. Now all you have to do, make up, and this is by inspection, class, make up 2 points such that they give us different functional vectors. So with that being the case, let's plug in 1 and 2 and observe. Again, this is by observation, class. This is by inspection. So when we do that, f of 1 is less than 0 and f of 2 is larger than 0. By the way, when we say 1 is 1 radian, I want to make sure everybody understands when we say f of 1 means, let me write it, 1 squared minus 1 minus sine 1, and it's equal to minus sine 1. I hope everybody understands 1 is 1 radian. 1 radian is about 57 degrees, and sine is positive in the first quadrant. With the negative, this becomes negative. Whereas 2, f of 2 becomes 2 squared minus 2 minus sine 2. Remember why this is positive. 2 squared is 4. 4 minus 2 is 2. 2 minus sine 2. What is sine 2? Sine of 2 radians, okay? Doesn't matter, if it's negative or positive. It will never go beyond 1. Remember that, right? Worst case is negative 1. By the way, it's not because sine 2, okay? But worst case is 1. 2 minus 1 still makes it positive. So that's why, even without putting it into a calculator, we should recognize this is positive. I hope everybody is following that, okay? And so with that being the case, we have shown that f of 1 is less than 0, less than f of 2. And by IVT, we do have a solution for this in between, okay? All right, class, we are moving to 2.6, limits at infinity and horizontal asymptotes. Okay. We looked at continuity and, in short, what it meant for us. Okay. The continuity tells us simply a function is continuous as long as the functional value and the limit are the same. So this is the bottom line. Okay. Every function is continuous in its entire domain as long as we can come up with a domain. And also we have the intermediate value theorem, the last piece we looked at. And what it really means is very simple. If you happen to have a continuous function in a closed interval, a continuous function in a closed interval, as it covers every point along the x-axis from that point A to B, if you will, okay? As it covers everything from A to B along the x-axis, it also covers every point along the y-axis from f of A to f of B. That's the idea. And if one of them happened to be positive, f of A and f of B, one of them happened to be positive, one of them happened to be negative, zero is in between. So that is used often to prove there is a root. Okay. The definition of a vertical asymptote was discussed. Now, definition of a horizontal asymptote, and we have seen this before in pre-calculus. The bottom line is what happens to the function, okay, as x approaches infinity or x approaches negative infinity, and that's really known as, if you will, the end behavior. So the terminology that was used, okay, for this concept in algebra was called the end behavior. I hope everybody remembers that. Okay. For example, if you have a quadratic function, the end behavior gives you the first and the second quadrant. If you have anything with an even exponent as the leading term. On the other hand, if it's a leading term that has an odd exponent, such as x cubed, those are the mean behavior, the first and the third quadrant. So when you look at this one, okay, the limit of f of x as x approaches negative infinity is negative infinity. The limit of f of x as x approaches infinity is infinity. This is something we are familiar with as far as the function y or f of x equals x cubed is concerned. Now, when we look at functions such as exponential functions, okay, remember what happens is that if the base is larger than 1, it looks like this. It's an increasing function. And you have a horizontal asymptote. Look at this definition. This means there's a horizontal asymptote here. The same thing here. That means there's a horizontal asymptote here. In this case, p is between 0 and 1. And in both cases, this one and this one, we have the horizontal asymptote, which is the x-axis, or y equals 0. Okay, this comes from this definition. Okay, so definition of the horizontal asymptote, we have seen it in pre-calculus, nothing brand new. Okay, class. I want to make sure that we are comfortable with that. All right, so now we are looking at more definitions. Again, you remember the vertical asymptote was discussed. Everybody remembers this was covered, okay, before. These are the vertical asymptotes. And we wrote, okay, that in this case, the vertical asymptote is x equals 0. Okay. Horizontal asymptotes, okay, so we have the definition of a vertical asymptote, reminding everybody what we have seen at the bottom. And as far as the horizontal asymptote, normally we have one. In the case of an inverse trigonometric function tangent, we happen to have two of it. Normally we don't, we have one. All right. So horizontal asymptote, vertical asymptote, we saw the vertical asymptote, the graphs, definitions, all of it from the previous exam. Now we are moving towards horizontal asymptote. finding the limit. And by the way, everybody remembers the technique when we are dealing with the rational expression where x is approaching infinity or negative infinity makes no difference. The process is the same, dividing by the highest degree term in the denominator. And I hope everybody can see that the highest degree term in the denominator is x squared. You divide and you get to this. Now, as far as I'm concerned, without the limit laws, and we're going to do the limit laws just for practice. As far as I'm concerned, class, right here, everything goes to 0 with the exception of 3 and 5. Okay, so right here you can say the horizontal asymptote as the equation y equals 3, and that's fine with me. Okay. However, for the sake of revisiting the limit laws, we can continue and look at the limit laws, see how it works. Okay, just for the sake of argument. So with that being the case, let's look at the limit laws. The limit law separates the top from the bottom, and then do it individually, and then plugs it in here. It's up to you. Now, the answer is 3/5. If you look at the graph, and by the way, 0.6 is equal to 3/5, okay? So if you look at the graph, when you take a limit of f of x as x approaches infinity or negative infinity, by the way, gives you the same result because the technique is the same. You divide by highest degree term in the denominator, namely x squared, to do the math, okay? And you end up with 3/5 in both cases. Again, I would have been happy done when I got here, okay? That's good enough, okay? However, we are looking at it from a graphical point of view also, just to be on the safe side. So infinite limits at infinity, we already saw this y or f of x equals x cubed. So as x approaches infinity or negative infinity, also the function may blow up to infinity or negative infinity. So it could be infinite limits. That's why we refer to it as infinite limits at infinity, okay? These are some functions that you are all familiar with as far as the shape y equals e to the power of x, y equals x squared, y equals ln x, y equals square root of x. Those are all elementary functions we have seen in previous courses. So this is a portion of it. By the way, e to the power of x class, it continues this way. Y equals x squared, take a look, it comes and goes that way, right? Y equals ln x goes that way. Y equals square root of x squared. All of them, when x go to infinity, they go to infinity, okay? But of course, some are faster than the others. Nevertheless, the infinite limits at infinity. Let's look at some examples. Let's start with part A. Part A and part B are both rational. And remember how we dealt with rational. It's very simple. We divide by highest degree term in the denominator. So in part A, the highest degree is t squared, okay, class? By the way, x, t, n, any variable is a dummy variable. So you divide by t squared. By the way, from here, class, you can go to this one. You're dividing by t squared. Okay, you don't have to write this, or you can say times 1 over t squared and write either way is fine. So you're here. So everything with the denominator t squared goes to 0 with the exception of 1. So everything else is 0. So why is this 0? Because the top is 0 and the bottom is a number other than 0. Okay. It is extremely important to remember when we plug in and we get to a number, okay, class, if that number is 0 over 0, infinity over infinity, or infinity minus infinity, and things of that nature are considered indeterminate. That means more 1. The second one, the highest degree term, is t. So we divide by t. And again, you can go from here, class, to here. I'm assuming everybody can do that easily. So with that being the case, what happens? Everything in that has a denominator t goes to 0, so you end up with t plus 2, 0. Now t goes to infinity, so on and so forth. So we write it as infinity plus 2 plus 0 over 5 plus 0. The numerator is infinity plus any number, infinity. The denominator is 5 or 5 billion, makes no difference. Infinity divided by any number is infinity. The only thing is, if the number is negative, it's negative infinity. So the sign, you want to be careful of, everybody, okay? But other than that, nothing to worry about. The sign you want to be careful of. All right. Part C, if you plug in, you get infinity minus infinity. And it is extremely important to know infinity minus infinity can go anywhere. It can go to 0, it can go to infinity, it can go to a specific number. So really it's indeterminate and we don't know the answer. And the technique involved in this case is simply multiplication by its conjugate. So when you multiply, x squared plus 1 comes out. Now x squared and minus x squared cancel each other and the numerator is 1. Now what is the denominator? Each one is infinity and simply infinity, and any number, no matter how large it is, divided by infinity or negative infinity becomes 0. Class, any number you divide by infinity, you get 0. Any number, again, we are looking at numbers, okay, not infinity, 5, 10, 10 billion, divided by negative infinity, the same thing, gives us 0. I hope everybody is comfortable with the concept. Okay. Yes.
For B, why did you divide by t? And then for A, why did you divide by t squared?
Okay, let's go over it one more time. What is the highest degree term in the denominator for the first one?
Squared, so 2.
What is the highest degree term in the denominator for the second one?
1.
T, exactly.
Oh, okay.
Divide by highest degree term in the denominator.
Okay.
Okay, does that make sense? Is everybody
Yeah,
okay?
that makes sense. Yeah, thank you, Professor.
My pleasure, absolutely. All right. Let's look at these examples. Remember what we do. We plug in and sometimes it works and that's absolutely fine, okay? So I hope you realize for part A, when you plug in, this is what you get. Remember, you have e to the power of negative infinity, which means 1 over e to the power of infinity, which means 0. Okay? Let me write that for you. I want to make sure everybody understands why this is the case, class. So when we say e to the power of minus t, we change it to e to the power of minus infinity. It's 1 over e to the power of infinity, which is 1 over infinity, which is 0. Okay, so a number, okay, a positive number larger than 1, 5, 10, 8, e to the power of negative infinity becomes 0. Now, I hope you realize in part B, when you plug in, you get infinity over negative infinity, because e to the power of infinity is infinity. So what is the technique? This is not a rational expression. But what technique did we use with rational expressions is very simple. We said we divide by highest degree term in the denominator. In this case, we divide by highest piece, highest value in the denominator, which is e to the power of t. So we are going to divide the top and the bottom by e to the power of t. This is the largest value. And again, you divide by e to the power of t and you can go straight from here to here, that's fine. You are dividing by highest degree term. In this case, it's not a highest degree term because it's not a rational, but by highest value term in the denominator. Highest value term in the denominator. So t goes to infinity. I hope you see that this 5 over e to the power of infinity, this goes to 0, plus 1. 4 over e to the power of infinity, this goes to 0, and this is negative 3. So 1 over negative 3, which means negative 1/3. I can't really emphasize this enough. I hope everybody is okay with that. Okay. So similar to rational expressions. Okay. Here's the next one. I hope you see if you plug in, you get infinity minus infinity class. So this is infinity minus infinity. Factoring is the key class. Factoring is the key. Now you have infinity times infinity minus 1, which is still infinity. So I hope you see that when you're dealing with infinity minus infinity, we really don't know what the answer will be, okay? It's indeterminate, and we have to use our algebraic techniques to fix the problem and get to the answer. Part D, we've seen this. The highest degree term in the denominator, x, divide by x, divide by x. Y, the highest degree term in the denominator. So when you divide by x, you get x plus 1 over 3 over x minus 1. Now replace it. The top becomes what? Infinity plus 1. 3 over x is 0 minus 1. Here's what you want to be careful. We know it's going to blow up to infinity, but because the denominator has a negative sign, it's negative infinity. And that's something that it is extremely important for everybody to see. Okay? Negative infinity. I want to look at one more page as the last part. Okay. One more page quickly. So pay attention to the practice that we are doing here and positive and negative. Now, when x approaches negative infinity, and I hope everybody remembers the concept, okay, that when you have a negative infinity, remember the square root of x squared. Let me just remind you, okay. Square root of x squared is equal to the absolute value of x. It's not equal to x. It's not equal to x. So it depends whether x is positive or negative, okay? So now, first of all, understand that x cubed is the same as x to the power of 6 under the radical, but it's positive or negative depends on whether x is approaching negative infinity or not. Now, so we can divide the bottom and the top by x cubed. There are two different ways I'm going to approach that. What I want you to see how what happens is when we take the x cubed in, okay? In case of the limit, when x approaches negative infinity, I put that up there, absolute square root of x squared equals absolute value of x, okay? And it becomes negative x if x is approaching negative infinity. That's important because minus x doesn't mean negative, it means the opposite of x class. And so with that being the case, okay, with that being the case, when you put it inside, okay, so x cubed is equal to square root of x to the power of 6 when x is positive, but it's equal to minus square root of x to the power of 6 when x is less than 0. I want you to really pay attention to this definition. I can't emphasize this enough. Okay, everybody? Okay. So now take a look at what happens. If I take it inside, I get x to the power of 6, then it creates a negative sign. Why is that? Take a look at this negative infinity. Take a look at this negative infinity. That's why. Okay, here's the second method before we finish it off. Okay, inside, take out x to the power of 6. So take a look at the second way. I want you to think about this when you go home and you practice with this. Second method before we finish it off. That one is not finished. So we can take out x to the power of 6. x to the power of 6 comes out as x cubed if x is approaching infinity. But because it's negative infinity, comes out as negative x cubed. That's because of the negative infinity, and take a look at the explanation. And now you can, this one, you can divide the top and the bottom by x cubed. This goes away, you see the answer. So this way, when you divide by x cubed, class, when you divide by x cubed either from here or from here, you get to this. Both result in this. And now what happens is this one goes to 0. You have square root of 4 with a negative in front. This goes to 0, you have negative 1 in front, and you get positive 2. Positive 2. However, I want you to look at number 22 and see the two of them next to each other. And I want you to go over this page at least a couple of times to distinguish between 24 and 22. 24, x is approaching infinity. So I can factor out the, I can divide by the highest degree term in the denominator. Please understand square root of x to the power 4 is x squared. So I can divide by x squared. And x squared is the same as square root of x to the power of 4 because x is positive. When it goes in there, we're dividing. Remember, x squared divided by x squared is 1. X squared, we take it in. This gives you x to the power of 4 over x to the power of 4, which is 1. This is 1 over x to the power of 4, which is 0. So you get 1 over 1. So I want to write this for you in case. So this part is, maybe you want to write this one, is equal to, this part is equal to 1 plus 1 over x to the power of 4 under the radical. Now you replace the x with infinity, the second part goes to 0, and the answer is 1 over square root of 1, which is